Now, a valid question you may ask yourself is, why do we still care about interference? Didn't we design FDMA and TDMA and CDMA to remove this interference? And the answer is no. So suppose that you have here a base station, and around this base station are some users. These users are communicating with that base station. Now, through proper design, for instance using TDMA, all these users will be mutually orthogonal, so they will not interfere with each other. So here things are okay. But of course there are other base stations in the environment. Maybe there's another one here. Another base station. And there are users associated with that base station. Oh, there's no inter-user communication, of course. And for this cell, everything is also okay, right? So all these users are also mutually orthogonal. But now what could happen is that this user here is using the same time slot as this user here. So that when the user 1 is transmitting to its base station and user 2 is transmitting to its base station, there will be some interference coming from user 1 to the second base station. And vice versa, of course. There will be some interference coming to this base station if users 1 and 2 are assigned the same time slot. So, for instance, TDMA 1 and 2 have same time slot. So for that reason, interference is important, and these metrics of SINR and SIR are also important. Now, a general cellular network will consist of many base stations, so that's what this picture showing here on the right. In red are base stations. With each base station you have a region, that is the coverage region of that base station. And then when a user is in one of those regions, like here, it will be associated with that base station. There are, of course, even more users than base stations. They're not shown in this picture. We will assume that there's a central controller that can coordinate something regarding those base stations. A base station serves a certain cell, so that is what is shown here, this kind of irregular polygon. And a user is associated with one base station. Okay, so when a user is in such a cell, we say that it's associated with that base station. Of course, in reality, cells may look a little bit different. A user monitors multiple base stations, so this means that even though the user here is connected to this base station, it may listen to some of the surrounding base stations. Like this, for instance. And by measuring the signal-to-noise ratio for each of these base stations, they can decide which is the base station to connect to. And then it can also make decisions regarding handover. So handover is the process of going from one base station to another. So if we here have a path of a user, when the user is in, let me try to draw this, in this cell here, it will be associated with the base station in that cell. When the user is then moving to another cell, like here, it will then become associated with the base station of that cell, and so forth. So this is called handover. Now, as a communication engineer, you may need to decide where should the base stations be placed and with what density. And here it's important to know that there's a trade-off between interference and rate. So this means that when you put base stations very close to each other, then users will be close to a base station. The rate can be very high. So let me try to draw that. So let's suppose we live on a line. We have a base station here, and we put our base stations like this. Then a user here will typically see a base station very close. So this means that the SNR will be very large. On the other hand, there will be many other base stations that are interfering to him. So this then means that the interference will also be really large. And if you don't have good coordination of these transmissions, that then implies that the SINR will be small, which then leads to poor performance, poor rate, or poor. On the other hand, if you decide to put your base stations very far away, then a user here will have very weak interference. Interference will be very small because these other base stations are so far they will not be able to interfere. But on the other hand, the distance to the closest base station will be large, so this means that the SNR will be very small. And then again, you have the issue that the signal to interference plus noise ratio will be very small. And again, you have poor performance. So you should mitigate this effect. And one way to mitigate this is to do something called frequency reuse. And this means that different base stations will be allocated different frequency bands. Okay, so let me then try to draw this. So that I have our frequency. I have a total bandwidth available, and then different base stations I will give different bands. So base station 1, 2, 3, 4, 5, 6. Or these are the bands. So this base station will get band 1, and this base station will also get band 1. And then another base station will get band 2, 3, 4, 5, and so forth. And by giving base stations that are having the same, by giving base stations the same band that are very far away, that means we're creating a scenario where the interference will be very small. And on the other hand, we can make sure that the users are close to each other, so the signal to noise ratio will be large. So by doing that, we can make an SINR that is really large, and this gives good communication performance. We will spend one slide to analyze this in a little bit more detail, and to do this, we will make an abstraction. So we will no longer use these kind of irregular cells, but instead use hexagonal cells, and then have a periodic reuse scheme so that there's a period in the reuse across space. So this is what then it will look like. This is called the hexagonal tessellation. So tessellation is just that you tile space with spatial reuse. And you have here all of these cells, and in the center of each of these cells is a base station. Each cell has a certain size here, which we call R, so that's the size of the cell. Each cell has a number, so from C1 through I guess 19 here, I see here. And this means that each cell that is labeled C1 has the same frequency band. Okay, and then C3, C2, C7, they have different frequency bands, non-overlapping. So there's no interference between any cell with C2 and any cell with C1. And if you do this in a periodic pattern, this creates a so-called clustering. So you see here that you have a cluster of cells, and all of these cells, they have different frequency bands. And then this cluster repeats. So I will try to draw this. So there's another cluster, I guess here, right, that uses the same bands. Another cluster here that uses the same bands. And with this clustering, we then have a so-called reuse distance. So that's the distance between the two closest cells that use the same frequency, and this is called D. And this is the same for any frequency that you choose. So if you look at frequency C16, then you will have this kind of gap here. Oh, that doesn't look very nice. This gap here, and this is also at distance D. Now, given the size of a cell and this reuse distance, we can compute the number of cells for each cluster. And this turns out to be proportional to, well, the size of the cluster, right, which is related to D squared over the size of the cell squared. So the area of the cell, and here's the area of the cluster. So you can verify this yourself. I don't want to do this here. Now we can compute the so-called cell edge SIR. So we assume that there's no noise, so I guess these assumptions are listed here. Same transmit power for all cells. Interference is dominated by the first tier. So this means that interference is limited by the cells closest around you. The cells further away, they don't matter so much. And we have only path loss with a fixed path loss exponent. Under these assumptions, we can compute the signal to interference ratio at the edge of the cell. Right, so we have a certain cell here. We have the base station here. We look at the user at the very edge. So that's the user that's in the worst shape because it will have the furthest away distance. So we'll have the largest possible path loss. For this user, this is the received power, right? So it's the transmit power times path loss, where this will be the distance d. And then we have the interference power, so that's the power due to the closest cells. Okay, I'm sorry, when I say first tier, I mean actually the first group of cells that have the same frequency band. It's not the group of cells closely around, because they don't interfere. So it's this group of 6 cells, 1, 2, 3, 4, 5, no, how many are there? Are 6, 1, 2, 3, 4, 5, 6 that are interfering with this cell. There are other cells further away that are also interfering, but they're so far away that we don't care about their interference. Good, and then the interference caused by those 6 cells with the same frequency is given by this expression. So again, transmit power with times the path loss, and here we have di, which is then this distance here, this big D. Okay, and then we can plug in what are the expressions for this distance and the distance to the first cell, and we find that we have, of course, this. So it's 1 over 6, and the 6 is because we have 6 interfering base stations. The ratio of the cell size over the reuse distance, and then here we have the path loss. Okay, so now we can change the signal to interference ratio by playing with R and D. Now, for communication, we typically want to have a minimum signal to interference ratio, so this should be greater than some threshold. And once we've decided this threshold, this then puts a limit on the number of cells per cluster. So by putting a certain threshold value here, we can solve for n with this relationship, and it turns out the solution is like this. Okay, so the more signal to interference ratio we want, the larger we should put n. Okay, so we should create larger and larger clusters. There's also 2 other performance metrics that we will consider. One is the user capacity, that's the number of active users per cell, and how we can compute that. So we see that here within each of these clusters, we have to divide up all of the bandwidth. We have a total bandwidth, let's say here, B, that we have available. We have per user bandwidth of BS, and a total number of cells for each cluster. So this means that here the bandwidth per cell is equal to the total bandwidth over the number of cells in one cluster. So that's the bandwidth we have available in one cell. And then we allocate a fraction of BS to one of the users. So that means the number of users per cell that we can support is the bandwidth per cell over the bandwidth per user. And this gives us some number. So we cannot support more users because we don't have enough bandwidth available in that cell. And this then gives you an indication how you should design your system if you want to support a certain number of users. There's also a notion called system capacity. Okay, these concepts of capacity are not capacity in the information theoretic sense, they're from a mobile network perspective. That's the number of channels you can create per unit area. So the number of users you can support per cell divided by the area of that cell. Okay, and then you can plug in these values and you obtain this. And then you see that when you reduce the size of the cell, we have smaller cells, of course. When we reduce, when we have smaller cells, we'll have more system capacity. When we reduce n, so smaller clusters, we'll have more reuse. We have to reuse the frequencies more frequently or more closely in space, and I will have more interference. So while these may seem a little bit abstract, I think it's good to do a simple example. So let's work on this problem where we have a system with hexagonal cells, 20 megahertz system bandwidth, 100 kilohertz bandwidth needed per user, path loss exponent of 2, and we want to have a signal to interference ratio of at least 10 dB to have good packet reception. And now you should compute the following things: the reuse factor, user capacity, and system capacity for 200 meter cell size. Okay. And then a more advanced question is, how should you design the system if you want to support a certain number of users per square meter, say 1 user per 100 square meter? And we will get back to this in the next part.